Is there any question about what we discussed on Tuesday? So this is the in vivo biomicroscopy we discussed on Tuesday. At that time, we mentioned that the fluorifer can be excited by photons with photon energy smaller than the gap. In theory, you cannot excite the fluorifer. But if you use femtosecond pulses, because you have a lot of photons, the photon density is pretty high, it is possible to excite the fluorifer accordingly. But I think it might be more helpful if I show you some view graphs. So I prepared something that is absent from your lecture slides. Okay? First, this slide shows what is fluorescence. It's very simple. You have some excitation photon. The photon energy should be big enough such that the transition is possible, right? And after that, the excited state will be relaxed to here, then relaxed to the ground state, and the difference of potential energy becomes the emitted photon energy. And by this view graph, you can compare the emitted photon energy is smaller than the excitation photon energy, right? So for example, this is blue light for excitation, but the emitted light could be green or even red because of the reduced photon energy. So this is the principle of fluorescence. Okay, then we can talk about two-photon excitation. This is a very straightforward comparison. The left-hand side shows one-photon excitation, very similar to the previous slide. You have excitation photon. Energy is big enough such that transition is possible. You have emitted photon with smaller photon energy. And the bottom one shows the focusing of the laser beam. And you can see over a large longitudinal range, within this area, every fluorifer can be excited because the excitation photon energy is big enough. So this area would be bright. If you use a detector, you can capture the emitted photons from all over this area. No depth sectioning is possible, right? But for the right-hand side, it's about two-photon excitation. Single photon energy is too small to excite to the excited state. But if you can combine two excitation photons simultaneously, okay, 1, 2, then the total photon energy becomes big enough. Transition is possible. Then you can see emitted photon. Okay? But in this picture, only a high photon density can do that. So if you focus a laser beam, only the area around the focal point, the photon density is big enough. And this excitation scheme is permitted. So if you use a detector, if you capture any emitted photon, it must come from this small area. No here, no here, okay? So you can have depth sectioning by two-photon excitation. And you can generalize the scheme to 3-photon excitation or 4-photon excitation and so on. The idea is very similar. Okay, so that's why if you use femtosecond lasers, you can have depth sectioning in microscopy. Okay, so I can show you one impressive picture. The left-hand side is single photon excitation. The wavelength of excitation laser is 488 nanometers. Okay, and if you focus the laser beam, what you can see? A large area is bright. a lot of fluorophores at different depths are excited simultaneously, right? So you cannot tell the photons, the emitted photons, come from which depths, no sectioning, okay? The right-hand side shows the same scheme, but this time the excitation wavelength is shifted to 900 nanometers, longer wavelengths. And this time, only a very small bright spot can be observed. So the captured photon must come from this small area. You have depth sectioning in this way. Okay. Any question? Yes.
那个右边那个情况是说，一定要同时两个光子给它能量，把电子打上去才行，要同时。
In theory, yes. 好，那这件事当然就不太容易发生，要同时，所以你一定要这个光子的密度非常高，这个几率才会够大，对不对？
因为想说 CW 是有可能先一个光子过去，把它激发到一半，然后另外一个光子再把它激发到最上。对，
但是 CW light 它的 intensity 比 femtosecond pulse 低很多，所以它的 photon density 会很低。它那个几率不能说0，但是就极低。啊，那你用飞秒雷射，这个几率就会足够高，高到让你观察得到。Okay, it's about probability. Okay. Good question. Any other question? Yes.
镭射光源是左右两个都来自于下方。
Let me see. Maybe from the top, you can see an objective here, right? 物镜，光可能是从上面照下来的。
光是从上。哦，所以它在大概可能也许焦距的地方的时候，它是最，因为它的那个。
Right. This is focal point. Right. Although there are photons here, but cross-sectional area is bigger, light intensity is not big enough. So almost no excitation here until the focal point. Okay. Other applications, because I just show you maybe 3 or 4 examples, but actually there are a lot of many. So I just summarize a little bit more. For example, high-speed optical telecommunications. Why it is useful? I mean, the femtosecond pulse is useful in telecommunications. It's very easy. If you use a single pulse to represent a bit, like bit 1, there is a pulse. Bit 0, there is no pulse. Then you can do communications, right? If the pulse width is shorter, then within a second, you can transmit more bits. So the bandwidth is increased, right? Very easy. So in experiment several years before, people reached 5.1 terabit per second for a single fiber, okay? So this is a very high transmission bandwidth. Do you know the transmission bandwidth of your smartphone, 4G service? Do you know the bandwidth? I think it's in the order of tens of megahertz, megabit per second, okay? Mega, and this is tera, so 6 orders of magnitude faster. So now you can sense how fast the telecommunication can reach, right? The second example is arbitrary radio frequency waveform synthesizer. Okay? Radio frequency usually refers to this bandwidth, tens of gigahertz, like 20, 30, or 50 gigahertz. Okay? If it's only a few gigahertz, then it's possible you just rely on the electronic devices. You can generate arbitrary waveforms. But if the bandwidth is even higher, like tens or even 100 gigahertz, electronic devices so far is not fast enough. So you need something else to achieve arbitrary waveform synthesizer. Do you know what is arbitrary waveform? Do you play with function generator in electronics laboratory? Right, you can push a button, you got sinusoidal wave. Another button, you got square wave, right? Another button, maybe you have sawtooth waves. But maybe just a few selections. Arbitrary means not only sinusoidal, square, sawtooth, but anything you want. That means arbitrary waveform. And you need arbitrary waveform, and the bandwidth is so high, it's usually very difficult. But with the assistance of ultrafast optics, actually we can do that. Let me show you one example. Okay, so this is also beyond the normal slice. I got this figure from a published paper. Okay, the idea is actually quite simple. Say you have femtosecond laser pulse here. Send the pulse into an optical pulse shaper. We might introduce the shaper technology in the following weeks. Okay? But the idea is it can help you to reshape the spectrum. Spectrum means signal in the frequency domain. For example, figure B, the horizontal axis is wavelengths. So from shorter wavelengths to longer wavelengths, you can manipulate the shape of your spectrum by the pulse shaper. Okay? Then you send the waveform, this one, into a dispersive stretcher, which we will introduce as well by the end of this semester. Okay? In practice, it could be very simple, just a spool of fiber. 就一捆光纤就可以了，够长的光纤就可以了。Then, as the output, you got optical waveform, but this time you strike the waveform onto a OE converter, usually a high-speed photodetector. And the purpose is O to E conversion, optical to electrical conversion. Then you got electric signal. And if you measure the electric signal, you will see a waveform exactly the same shape as the optical spectrum. Okay? Remember now, figure C, the horizontal axis is time, not wavelength. So this is a time domain signal. This is a frequency domain signal. Okay? So if you want any time domain waveform, you just create the same thing in the frequency domain by a shaper. Then with this simple scheme, you got arbitrary electric waveform in the order of tens of gigahertz. This is 1 nanosecond. So if there is one cycle, it means 1 gigahertz. But you can see within 1 nanosecond, you have several cycles. So that means the speed of the waveform is faster than 1 gigahertz. It's several gigahertz, and it can be even faster. Okay? So you cannot imagine this is something simple square or sinusoidal wave. It's a very complicated waveform. You can generate them by the simple scheme. Okay, any question?
How did the ripple, like the one that is added -2 nanoseconds, come from?
Here?
Something like, how did it come from? Did it come from noise or?
It could be imperfection either here or in OE conversion. Yes. If your photodiode is not fast enough, then even you strike a perfect waveform, the response curve is not perfect. Okay. So it still relies on fast photodetector. Yeah. But photodetector now is pretty fast. You can get more than 100 gigahertz photodetector. But the waveform generation speed is still much slower than photodetector. So we can borrow the, I mean, there is a margin in between. Yeah. Third example is three-dimensional microfabrication. Okay. For example, microfluidic biochips. Okay, so it's about fabrication. 就是微奈米尺寸的这个制造Let me show you another example. Hopefully, the fabrication precision can be beyond the diffraction limit. What is diffraction limit? If you studied diffraction, you must know the famous rule. There is diffraction limit. A beam, no matter how strong you focus it, the size is limited by this one, right? Wavelength over 2 times numerical aperture, right? I assume you have known this formula. And the numerical aperture could be in the order of 1. So roughly speaking, it's half of the wavelength. It's your diffraction limit. So usually the visible light, the wavelength is hundreds of nanometers. So diffraction limit should be something like 400 nanometers or 300 nanometers. That's the limit. You cannot focus a spot, visible light spot, even smaller than that one. But can we use laser technology to fabricate something that the line width or precision is even smaller than that limit? Okay? And it has been shown that is possible. Like this example, it comes from a website of a German company, Nanoscribe. They fabricated this Eiffel Tower. Of course, there is no scientific purpose, just for demonstration, right? And this bar, the length is 100 microns. And you can see some fine structures are even smaller, much smaller than this bar, right? Actually, the precision of Nanoscribe is already 150 nanometers, which is smaller than the diffraction limit, okay? So you can imagine with the femtosecond laser tool, you can do something pretty cool, right? But why the diffraction limit can be overcome? For example, this is a light intensity distribution of your focused spot, okay? Usually this is referred to the spot size limited by this one, right? Lambda over 2. But when you do fabrication with femtosecond lasers, whether the material has reaction to the laser light, there is a breakdown threshold here. If you will control your light intensity peak such that the peak intensity is very close to the threshold, then only this area there is reaction because it's above the threshold. For the remaining, there is no reaction. Okay? Then you got the machining size in this order, and it could be much smaller than the spot size, right? As long as you can well control your light intensity, and this threshold is a hard limit, either on or off. There is no transition. Then you can do that, right? Traditional lasers machining, there is no clear hard limit threshold because it relies on the heat. 传统的雷射加工没有这个 threshold， 它是靠把雷射光的能量吸收变成热 ，evaporate the material. And you know the thermodynamics is about probability, right? So it's never a hard limit. But this is so-called cold machining, 冷加工. It's nothing about heat. It's about nonlinear optics or nonlinearity of the material. There is a hard limit. Then this scheme can be realized. Okay? So now it becomes a very popular machining technology because you can do very small, very precise. Plus, it can be three-dimensional. That means you do not have to create the structure from the surface. you can directly create structure from the middle, beneath the surface. As long as you can focus your laser spot within the volume, you can do that. Okay, that's why it's three-dimensional micro or even nano fabrication. And usually it's material independent. As long as light intensity is big enough, anything can be machined. Anything. Like glass. Traditionally, we suppose glass is transparent, right? So there is no absorption about light. Even you shine a very intense laser beam, just pass through, no machining, right? But with femtosecond lasers, even glass can be machined. Okay? So this is something very popular for the mechanics. Okay. Any question?意思就是 for example, 超过了这个 ratio， 键结被你扯断了，这个材料的性质被改变了，不超过就没断，就没改变，所以这是一个 hard limit。
所以它是一个要看什么材料的什么特性。
对对对 ratio 会跟材料有关，但是任何材料都有一个 ratio， 而且都是 hard limit。So it becomes a very flexible technology. Traditional laser machining, you have to carefully choose the laser wavelengths such that the material to be machined can absorb the laser light, right? Like you want to cut the steel. Maybe you choose CW lasers, 10 micron wavelengths, because steel will absorb 10 micron wavelengths. But with this scheme, you don't care about the wavelengths. As long as the laser is intense enough, it can do machining for almost all materials. Fourth one is laser accelerator. I think it's of interest for the physicist. 物理的人可能很有兴趣，加速器。Fundamental physics, you want accelerator. But traditional accelerator using radio frequency technology, the acceleration could be tens of mega instead of giga, electron volt per meter. That means traditional accelerator with 1 meter length, it can accelerate the particle to tens of giga electron volt. But with femtosecond laser as acceleration, it can increase 1,000 times, 1 meter per giga electron volt. So the size can be reduced by 1,000 times. 所以1公里长的传统加速器可以变成1公尺长的雷射加速器。Okay, so you do not need a large land construction to create accelerator if you use femtosecond laser as your driving source.